Hi, my name is Kathleen Coleman, and I'll be talking about Physics 2212, Lab 4, about circuits. Here's a little outline of what I'll go through. So I'll start with an introduction, and then I'll go through charge conservation and energy conservation in series circuits, and then RC circuits, and then time-dependent voltage across a discharging capacitor, and then I'll answer some discussion questions. The purpose of this experiment was to predict the behavior of circuits with resistors in series, use multimeters to measure the values of current and potential difference, and examine the behavior of ohmic resistors and capacitors. One of the fundamental principles you need to understand is Ohm's law, which says that delta V equals I times R. Also, you should understand the loop rule, which says that the sum of all of the voltage drops across the loop is 0. Energy and charge conservation, equivalent resistance in series, which says that the total resistance of some resistors in series is equal to just the sum of the resistances. You should also understand batteries, resistors, capacitors, ammeters, and voltmeters, how to linearize the data from the experiment as well. My main result was that RC experimental was 7.067 seconds and RC true was 6 seconds. We start off with this simple circuit with two resistors in series, and we need to find the current going through both of them. So I used the loop rule and Ohm's law here, and I predicted that I1 and I2 would both be equal to 0.02 amps. Put this into the simulation to make sure this was correct, and it was. But what if one of the ammeters was inserted backwards? And we'll see that nothing changes. I1 is still I2, and they're still both 0.02 amps. But what if we replaced one of the ammeters with a voltmeter? Now we do have a change. The voltage drop across the gap will be -3 volts. Also use the loop rule to figure out what the voltage drop across each component of the circuit will be. We'll see that for most parts of the circuit, it's actually going to be 0, but the voltage drop across the battery will be +3 volts. And then we have a voltage drop across the first resistor of -0.959 volts, and then across the second resistor of -2.041 volts. Here we have a plot of the voltage drop. We can see it starts at 0 and ends at 0 as expected. And here's a question about when you attach the voltmeter, you alter the circuit. So why does the ammeter reading change? And this is because the voltmeter has a very high resistance, so very little current will actually flow through it. We add an ammeter in parallel with the 100 ohm resistor. Well, the ammeter has a very, very low resistance in contrast to the voltmeter, meaning that almost all of the current will go through the ammeter instead of the 100 ohm resistor, effectively lowering the total resistance of the circuit from 147 ohms to 47 ohms. And we can see that the math checks out here. It should be 0.06 amps as the current, and it is according to the simulation. Also experimentally find the resistance of each circuit element by rearranging Ohm's law. So here is the video of the battery, 10 ohm bulb, and capacitor all connected in series. And on the left we have it charging, and on the right we have it discharging. So it took 15.27 seconds to charge and 15.24 seconds to discharge. They're about the same. There's some experimental error there with the time it took me to click pause and stuff. So now we have pretty much the same thing, but with the 20 ohm resistor this time, and we can see that it took significantly longer to charge and discharge, taking 27.45 seconds to charge and 27.56 seconds to discharge. So now we have a setup similar to what we had a moment ago with a 9-volt battery, a 0.2 farad capacitor, and a 30 ohm bulb all connected in series. So basically what I did is I paused the simulation about every 2 seconds as the capacitor discharged, and also I had a stopwatch. So I got a value for the V about every 2 seconds, and I did that for 20 seconds. And so then I could calculate Ln of V over V naught being 9. And then I plotted that versus time. And then the slope of that is going to be -1 over RC experimental. So we can rearrange, find RC experimental, which I found to be 7.067 seconds, and my true value to be 6 seconds. What if you did this lab with a real ammeter? Well, a real ammeter does not have zero resistance, so when I connected the ammeter to the resistor in parallel, some of the current would have gone through the resistor. But in the virtual experiment, none of the current went through the resistor since the ammeter's resistance was zero. And what if we did the experiment with a real battery to charge the capacitor with no resistor in the circuit? If there was no resistor in the circuit, our model would predict that the capacitor would charge instantly. However, real-life batteries have internal resistance, so the capacitor could not really charge instantly.